So thanks all for being here. Thanks, Mike, for speaking at the TCS Plus seminar. So Mike was a PhD student at Stanford University, advised by Omer Reingold. He's been working and doing a lot of very impressive work on fairness and computational complexity and the interplay between the two. And I think it's public now given the slides. So he's gonna join the UC Berkeley in the fall, I think, as a Miller Fellow. Yeah, and today he's gonna tell us about evidence-based fairness. And I'm pretty excited to hear about it. Just before the talk starts, I'd like to thank all the organizers of TCS Plus. I'm only one of them. There's a whole team behind. And also announce the next talk. So our last talk of the season is going to be next week, and it's going to be Cliff Stein from Columbia University, who's going to tell us about parallel approximate undirected shortest path. That's all I'm going to say for now, and I'm going to leave the floor to Mike. So thanks, Mike.
Thanks, Clement. Can everyone hear me? Okay, great. So I wanted to just start by saying that I know there's a lot of things going on in the world right now, and I appreciate that you're able to tune in. I think it's important for us to affirm, even in our professional spaces, that Black Lives Matter. And over the past few days, I've been thinking a lot about how I can be a more active ally, and I encourage people to do the same. I have more questions than answers at this point, but my experience is that the toughest questions typically are solved collaboratively. So please reach out if you want to chat about that. With that in place, today I'm going to tell you about some other collaborative work, work on what I'll call evidence-based fairness for today. I sort of changed the title last minute on Clement, so sorry about that. But good, so this will be based on joint works with Cynthia Dwork, Ursula Hebert-Johnson, Omer Reingold, Guy Rothblum, and Galiona. So these days, I don't have to tell this community that algorithms are sort of everywhere you look. Algorithms are making medical diagnoses. They are making, predicting the content that we want to see. They're driving our cars, and they're running sophisticated online advertising platforms for us. And algorithms have even entered the public's consciousness, perhaps best illustrated by this New Yorker cartoon. And there does seem to be a growing recognition that algorithms are having a profound impact on our daily lives. And while algorithmic systems have a potential to have really great and amazing impacts on society as a whole, unfortunately, for every headline you see highlighting some impressive algorithmic performance, you also see headlines like this, highlighting the bias and unfair discrimination that can be baked into algorithmic decision-making systems. And across many different domains, algorithmic bias seems to be everywhere and really suggesting a pervasive societal issue. One particular case study that I think is illustrative is this so-called gender shade study. So in this work, Boulomini and Gebru studied facial detection algorithms, sort of machine learned image recognition systems that were meant to detect faces on people. And so they looked at a few different commercial systems, but really the findings seem to be very broad. And so in general, these systems tend to perform very well overall on average. We found that they had 90% accuracy at a certain gender detection task. But then you look a little bit more closely and you see that actually they're more accurate on men than on women. And you look a little bit more closely and they're more accurate on white people than on Black people. And you look even more closely and you see that in fact, they're achieving nearly 100% accuracy on white men and close to random guessing on Black women. And so this study really made concrete the types of systematic biases and discriminations that can be present in these systems, resulting in significant utility and error discrepancies across different significant demographic groups. And so the types of questions that one might ask given these situations is, can we improve the performance of these types of predictive models or algorithms on underrepresented groups while maintaining the overall performance? So our approach in general, I don't need to preach to the choir here, but our approach will be a formal one. And we're going to try to formalize what's going on in these systems and the unfairness and bias that we're observing using the language of theoretical computer science. And importantly, we're going to emphasize abstraction, trying to make sure that we capture the salient elements of the problem in a way that captures the essence, but really allows for general purpose solutions. And also emphasizing mathematical definitions so that we know what we're talking about precisely rather than just intuitively. And the eventual goal of the whole research program would be to provide some sort of provable guarantee of fairness of the system. Very much in the same way that modern cryptography provides a provable guarantee of security. And so most existing works in this field study questions surrounding prediction, like the prediction task that I was talking about in the last few slides, and not on ranking. But I want to argue that ranking is actually a very natural problem to study as well. And so why should we study rankings? Well, rankings are often the underlying impetus for risk prediction. For example, you can imagine that Stanford or UC Berkeley or whoever is running college admissions. And perhaps they're going to estimate some probability of, for every student, that they'll graduate within the next 4 years. And then after that, they're going to always select the top 1,000, 10,000, however many applicants, and grant them admission. Well, really, this estimation procedure was not, they didn't really care about the probability of graduation with 4 years. What they really cared about was some rank ordering of the individuals and according to their qualifications. So really, prediction was a proxy for getting at this underlying ranking. Another reason to study rankings is that rankings tend to be at the heart of some legal approaches to affirmative action. In particular, in the states of Texas and California, there's certain what they call top 10% rules, where the top fraction of graduates from high school classes, from all high school classes, are automatically granted admission to state-funded universities. And this is a form of affirmative action, but importantly, underlying it, there's some ranking. You need to rank the individuals at every high school. And so there then becomes questions of fairness and discrimination within these rankings as well. So the other reason we might want to study rankings is that there is some tight connection between the task of prediction and the task of ranking. And so studying ranking may actually give us a new lens on the prediction tasks that we often care about. So perhaps we can come up with some natural desiderata for rankings and try to understand when these desiderata would be satisfied by certain classes of predictors. So to give some intuition for how predictors and rankings are connected, consider the fact that basically predictors induce rankings. So if we have the following predictions where there's a group of individuals getting a score of 0.8, a group getting a score of 0.5 and a group getting a score of 0.2, then we can translate this into a ranking just by respecting the rank induced by the predictions. To see the reverse connection, we can see that rankings often suggest a set of consistent predictors. So for instance, if we started with this ranking, then we could go back to roughly the predictor we had before, but we could also move these predictions around to various other points in a way that would still preserve the rank ordering. And so this is meant to be intuitive and a high level at this point, but to suggest that there does seem to be some connection between the world of prediction and the world of ranking. And so the questions that we'll ask in this talk are about questions of fairness in both prediction and in ranking, and asking when do fair predictions actually induce fair rankings, and asking whether fair ranking is somehow necessary to achieve good fair prediction. And specifically, we're going to discuss two different notions. In the predictor world, we're going to start by talking about this idea of multi-calibration, which is a notion of fairness that I'll get into in a minute. In the ranking world, we're going to talk about a notion that we call domination-compatibility. Again, it's a notion of fairness, but this time in rankings. And for those of you who don't like spoilers, you should plug your ears, but so here's your spoiler alert. In fact, we're going to see that even though we define these notions in very different worlds, one in prediction, one in ranking, there's actually a very tight connection between these notions of multi-calibration and domination-compatibility. And so this sort of gives us both algorithmic insights as well as insights into the structure and requirements of these fairness notions. So that's sort of the highest level overview of what we're going to do. And now I'm going to jump into some of the more technical details. Feel free to interrupt me if there's any questions at this point, but I'll keep moving until I'm interrupted. Great, so just so that we're all on the same page, want to set up some notation and set up a problem in your mind. The types of problems that we'll be thinking about today will be supervised learning problems, where you're given a bunch of examples, or maybe not a bunch, but a small set of examples of XY pairs, where X is distributed according to some fixed but unknown distribution D, and Y is the outcome variable. We'll think of it as binary. And Y is distributed according to Bernoulli of this score that we'll call P star. So P star of X represents sort of the conditional probability given X that Y will be 1. And so this is a very standard pack learning setup. And if you want to have a concrete prediction task in mind, perhaps you can think of being given images and wanting to predict the probability that the image of some skin lesion is benign or malignant. But so throughout, I'm going to, the one important thing to think of, to keep in mind is this notion of P star. P star will represent the Bayes optimal predictor. And our goal will be to recover a predictor that estimates P star of X according to some notions of estimation. Good, so the standard objective in supervised learning is generally to minimize some average error, minimize the population risk. The concern, however, though, is that this is a very majority-centric objective. Faced with trade-offs that the algorithm may have to make, the learning algorithm will bias its decision towards the majority simply because they are a majority. They're the largest population. So it's natural then to ask yourself and pose instead questions of, rather than optimizing this fixed objective, asking for notions of fairness. So perhaps the most intuitive and most natural notions of fairness are these so-called group notions of fairness. And I've written up a general recipe for a notion of group fairness. The first step is to identify a statistical quantity of interest. And then once you have some statistical quantity, to define groups based on some sensitive attribute, either race, gender, sexual orientation. And then once you have your notion of sensitive groups, to ensure that this statistic looks right across both the majority groups and the protected groups. The appeal of these notions is that they're sort of intuitive and easy to work with. So one notion in particular that we'll focus on today is the notion of calibration. Calibration tries to capture the idea that predictions should mean what they say. One way to think of this is that 70% of the images of skin that received a score of 0.7 would end up being positive, malignant for cancer. More formally, we say that a predictor is calibrated if the predictions are unbiased, even after conditioning on the group that received a certain score. So what do I mean by this? Let's say it one more time. So what we're going to do is restrict our attention to the individuals who receive score V according to this predictor P. And now amongst these individuals, we're going to take the expectation of their true qualifications. And this expectation should be approximately the score that they received, V. And this should hold not just for 0.7 and 70%, but for all the scores given out by this predictor. I want to say for simplicity in this talk, I'm going to focus on the case where the predictors are supported on a discrete and finite support within 0, 1.
So just a small question on the guarantee. Here, like the approx symbol, is it like a multiplicative, additive guarantee? Because additive would be much less meaningful for populations that have a small probability, right?
Right. So actually, so in this definition, it will be additive, but it will be additive sort of over the conditional distribution. So, for instance, if only a very small fraction received a certain score, then it's normalized according to the size of that group.
Okay, thanks.
Yeah. Mm-hmm. But of course, you could define it either way. Good. So good. So why did this? Why is calibration a notion of fairness? Well, the idea is that the predictions should say what they should mean what they say, regardless of what group you're in, whether you're in the protected group or whether you're in the majority group. The problem, of course, though, is that these predictions might not say that much. So in particular, our concern is that this group notion of fairness, called calibration, may allow predictors to stereotype in a certain sense. So let's go through a toy example. I'm going to assume that S and T, I have two groups, S and T. S is the minority group, and that actually they're identically distributed according to P star. Half the individuals are ones, half the individuals are zeros. But I'm going to give them out very different predictions. In the group T, I'm going to give out perfect predictions. P is going to match P star. But in the group S, P is going to be quite different from P star. It's only going to give out the average value to the entire group S. So even though these predictions look very different, we can observe that the predictions are actually calibrated, even though they ignore all variation within the group S. So to verify this, we have to go through the different values that were predicted. So amongst the individuals who receive score 1.0, in fact, their expectation is 1.0. Amongst the individuals who receive score 0.0, in fact, their expectation is 0.0. And then amongst the individuals who receive score,
yeah, Michael, I missed two questions. So Shaha was asking what happens when the scores are continuous, because there is a conditioning that
Yeah. Great. So it's a good question, and so you have to work with a discretization of the space. It's you have to be careful. I don't want to get into all of the details today, but for now, you can think of the scores. You can enforce on yourself that you're going to work with predictors that are working over a discrete space.
Okay, and there was another question I missed. There was a question asking, is it true that for every predictor P, there is some sensitive attribute for which P is completely uncalibrated?
Could you repeat the question one more time?
Is it true that for every fixed predictor P, there's going to be some attribute, sensitive attribute, for which P will be completely uncalibrated?
No, actually. So in fact, so I should just jump back. So, okay. Way too far. Good. So, in particular for the predictor P star, suppose that we actually were able to get our hands on P star, then P star will be perfectly calibrated for all groups over all, any condition you make, P star will be perfectly calibrated. And so in a sense, the best thing that we could hope for is P star, and it will, getting there is the question, and getting some reasonable approximation, even if sort of this Bayes optimal, this statistical optimal is computationally infeasible. Okay, good. So I'm gonna let my animations run. And good. So we were verifying that these predictions actually are calibrated. And so the final thing to do is to look at the individuals who receive score 0.5. And amongst these individuals, half of them are ones, half of them are 0. So in fact, their average score is 0.5, even though, again, these predictions ignored all variation within the group S. And so this type of algorithmic stereotyping runs the risk of ignoring or overlooking qualified members in minority populations, where the individuals in S, they were identically distributed. There were plenty of qualified members in S, but selecting a fixed threshold ignored them and only selected individuals from the group T. And so the concern is that group notions of fairness provide very weak and only on average guarantees, and not to individuals. And in fact, they may not even provide meaningful protections to the protected groups. So a very different approach to fairness, a very different paradigm, is this idea of individual fairness, which was introduced in a work called Fairness Through Awareness at ITCS 2012. And it's really motivated by the shortcomings of group fairness notions, that they allow you to effectively overlook variation in the populations, in, say, the minority population. And the guiding mantra here is to treat similar individuals similarly. And the notion of similarity is defined by a certain task-specific fairness metric. And what this does for you is two things. On the one hand, it provides very principled and strong protections for individuals, which is what we really want. We would love to give every individual who shows up a guarantee of fairness. The challenge, though, is that it requires you to get your hands on one of these task-specific fairness metrics. And so there's been a lot of nice work in recent years trying to answer this question of how do you get around this obstacle of where's the metric come from. But I want to propose a different paradigm for fairness. So somehow we have these two extremes. We have these group notions of fairness that are easy to work with, but only give marginal guarantees. And then we have this other paradigm of individual fairness that somehow captures a theoretical ideal, but has practicality issues. What I want to ask is what's in between? Can we strengthen the guarantees of group fairness while maintaining the practicality? And so our idea is to go beyond protected groups and specifically to enforce calibration across not just the so-called protected groups, but across subpopulations. And so this leads us to a definition. We'll say that given a collection of subpopulations, C, a predictor is C multi-calibrated if the predictions appear to be calibrated not only on the population overall, but even after we restrict our attention to some subgroup within our collection of subgroups. And we'll require this for all subgroups, G, in our collection C. So, right, so colloquially, we can say that multi-calibration captures the idea that predictions should be calibrated across a rich class of subpopulations. So instead of just protecting Black individuals or women marginally, what we're going to try to do is protect Black women who wear glasses. And interestingly, it seems that even protecting an attribute that doesn't seem sensitive, like wearing glasses, may help identify structure in the protected groups of interest and help to protect these populations. So the observation is that increasing the complexity of this class C really strengthens the multi-calibration fairness guarantee, where complexity in C requires understanding not just the population overall, but the variability within the protected groups. So,
Mike, can I ask a question? This is Sam.
Yeah.
How does this relate to? It seems like closely related to just improving your accuracy on the protected groups.
Yeah.
So, and also in your example that's now back up on the slide, this would have been fixed if you had been more accurate in the red group as well.
Right.
So how can you say how these things are related?
Yeah, absolutely. So good. So multi-calibration and calibration in general is sort of an accuracy-based notion of fairness. It is advocating that the first thing you need to do before trying to do any sort of corrective discrimination or corrections of the probabilities themselves is to understand your populations as well as possible. And the challenge, of course, is that when you're working with, say, a fixed hypothesis class, there may be trade-offs that end up getting made between different groups. And these trade-offs may end up hurting minority or underrepresented populations. And from a small set of data, you may not understand the small subpopulations as well. And so what we're saying is that that's not acceptable, that you really do have to go in and do your best to understand not just the population overall and not just the majority group, but really understand and make better predictions within the minority group. And multi-calibration is one way to formalize this.
Okay, but you could force yourself to make better predictions or the best predictions possible in the minority groups by replacing mean square error by min over groups mean squared error on the group, or something much more heavy-handed than that. This is much more heavy-handed than multi-calibration, but presumably there are drawbacks to this. So why wouldn't you just replace your notion of accuracy with something that's sensitive across groups?
Yeah, so that's a great point. So there are works that do exactly what you just proposed, that try to do some sort of distributionally robust optimization, or try to basically say that what we want is to minimize the max violation across groups. What we argue and you could do this. The problem, of course, is that this then leads to other trade-offs, where now you have that the predictor that's best on some small group may be very bad on other groups. And so what we're going to show is that actually there's a way to achieve multi-calibration in some sort of boosting-like fashion that actually improves accuracy and improves the calibration across all of your identifiable subpopulations, all of these populations within C simultaneously.
Great, thanks.
Great. So getting further into this intuition that Sam's bringing up, the idea is that this class C that parameterizes multi-calibration really should try to help you identify relevant structure to your prediction task. So for instance, if we had had a group in our class, G, that maybe would represent this subpopulation, then we can now hone in on this and observe that the predictions, even though they were calibrated overall, and even though they were calibrated on the population S, they're not calibrated on this group G. The predictions 0.5 are very far from the expectation on this group. And so this would force us then to make better predictions within this group. And calibrating on the subpopulations defined by our groups G and our collection C would force us to somehow have a better global understanding of the population as a whole. And so again, this is a toy example, but hopefully it gets across the intuition. The question, of course, is which subgroups should we and can we hope to protect in this class C? The ideal thing that we would want would be to give an individual guarantee, to say that actually we could get our hands on this P star and make perfect, or the best possible predictions that we could. But from a small sample, this is actually statistically impossible. And so we have to make some sort of compromise. And the compromise that we propose is to audit and to make sure that you're calibrated on large and what we call efficiently identifiable subgroups. So in particular, we can think of defining this class C via a complexity class or via a concept class, if you're a learning theory person, which is to say that these groups should have a succinct description and should be learnable in a certain sense. So formally, we can somehow bound the complexity of implementing this characteristic function. So perhaps you would want to audit on small conjunctions or on small decision trees or linear functions, these kinds of classes. So for instance, perhaps we would have some group GI that's defined by this conjunction. But then there would also be a different GJ defined by another conjunction. And really, we could keep going. And the point is that we don't want to just enforce it for a small handful of groups or a small handful of conjunctions, but for all of them simultaneously. And so this complexity really helps understand the population and subdivide it and improve accuracy across the population. But then the question that we have to ask is, when can we achieve this? How much of a burden is this using a complex C going to place on us? And so our main results from this earlier work from ICML 2012 is that multi-calibration actually is achievable for certain classes that we call identifiable classes. So what do I mean by this? So statistically, multi-calibration is achievable, which is to say that a small sample suffices, a small set of labeled examples suffices to achieve multi-calibration, at least information theoretically. So this theorem requires that these groups be sufficiently dense within our population, but then what we're able to achieve is sort of the sample complexity that you would expect. Logarithmic dependence on the number of groups that we want to protect, and polynomial dependence in the size of the groups, as well as our additive accuracy parameter. And so while this theorem statement may look familiar based on what you know about learning theory, I want to argue that it's actually somewhat non-trivial to achieve. And why is this? The challenge is that these multi-calibration constraints are actually adaptively defined statistical queries. So in particular, we need to condition on these groups that are defined by the predictor in question. So while we are learning a predictor P, we are simultaneously conditioning on and asking statistical queries about groups that are defined by the predictor that we're working with. So in other words, the queries that we're asking somehow already depend on the data that we've looked at, which is a huge no-no in classical statistics and generally leads to overfitting and can lead to statistical invalidity. And so the way that we get around this is actually by implementing our learning algorithm using differential privacy. So this leverages a connection discovered and improved in a recent line of work that connects the idea of statistical generalization to differential privacy, and showing that if you implement if your learning algorithm is differentially private, then it generalizes well. And so that's all I want to say about that, but I'm happy to answer questions about it as well. And so some very recent works have looked at a different approach to bounding some sort of multi-calibration loss, but that gets around this differential privacy. Qualitatively, the results are somewhat different, but there's new works coming out towards this as well. I also want to mention that computationally, then there's a question of, can we learn these things efficiently? And so the high level takeaway is that multi-calibrated learning actually reduces to machine learning. What do I mean by this? Well, actually these problems see alpha multi-calibration and is actually polynomial time equivalent to the task of agnostic learning, the class C. So how should you interpret this theorem? It's sort of a good news, bad news theorem. The bad news first is that agnostic learning is a notoriously hard problem in theoretical computer science. And what this equivalent says is that there's no way to get around that. That in the worst case, for arbitrary classes C, you're likely to have to essentially enumerate over the groups in your class in order to achieve multi-calibration. The good news, however, is that essentially all of machine learning and practical machine learning is so-called agnostic learning. We don't actually believe that the world is realizable by the classes that we use to learn, and yet we're still able to learn very effectively. So what this says is that in practice, we can expect that we may be able to audit and learn for multi-calibration quite effectively, and more effectively than we would expect to in theory.
So Mike, I've got a small question about the second point, about the good news. So, okay, it's good news because even though we know it's hard in theory, worst case, agnostic learning in practice seems to perform well. But like, when we learn something that way, like we can actually test it on the test set, etc. For the multi-calibration, if something fails, can we detect it? Like, can we also do that?
Yeah, so good. So not obvious. So the first answer I would give is no. That if your algorithm that you're using is a heuristic, you're sort of stuck with the heuristic guarantees. It's a good question of whether when one could get sort of provable guarantees of sort of certification, but I think even the certification problem is going to be equivalent to agnostic learning. So I don't expect that. I think you're correct that it's a little bit unsatisfying.
Thanks.
So to give some high-level intuition for how this algorithm works before getting into, basically the way that it works is it's an iterative algorithm that is going to essentially reduce the problem of learning to auditing, and auditing for a miscalibrated group within our class C. And so this is why actually a learning algorithm for the class C can help you. That essentially you're going to create labels out of your current predictions and out of the labels in your data set to encourage the learning algorithm to find a group that is currently miscalibrated. And then you're going to, once you detect a group, you're going to sort of nudge the predictions in the correct direction. And so it will be iterative and improve the calibration on some groups until eventually, after not too many iterations, you can show that basically via some sort of gradient descent style argument, that eventually without your composite function will be multi-calibrated. And the claim is that this sort of multi-calibration boosting or multi-calibration updating actually improves the accuracy on these identifiable subpopulations without hurting the overall accuracy and without introducing trade-offs. I want to briefly mention that multi-calibration is one of a number of definitions that is sort of now trying to bridge this gap between group notions of fairness and individual fairness. We've been calling them multi-group fairness notions, where the goal is really to enforce these group notions across as many subgroups as you can simultaneously. The goal being to maintain feasibility while strengthening the guarantees of these fairness notions significantly. Good. So now I want to get back to this question of ranking and saying, okay, so now we have this very strong notion of fairness in prediction, but we want to translate it into a guarantee and understand whether we can just translate it into a guarantee on of fairness in ranking. And it's not obvious at first. Even though there is this connection between ranking and prediction, it feels that the goals of ranking are somehow qualitatively different from the goals of prediction, where the relative ordering is really important rather than these absolute scores. And ranking really does feel like a global task. If you introduce a small inaccuracy here, then it may actually propagate and affect the entire ranking. And so again, it will be worthwhile to think about fairness notions within our study of ranking, and different than the ones that we discussed in prediction. So to switch gears, I want to give a little bit more setup for this question of rankings. So what are we even talking about? Well, again, we're going to assume that our features are distributed according to some fixed and unknown distribution D. And we'll say that a ranking, we'll define a ranking essentially as some sort of almost a CDF, where we want to say that a ranking is a function from the universe of individuals to 0, 1, where for all tau, for all thresholds, the probability that an individual, a random individual over the distribution receives score less than tau is tau. If that doesn't make sense, then I think it's almost a CDF, if that helps. And so the idea will be that we're going to rank individuals. We'll show it visually that the top rank will get 0, and the bottom rank, the sort of worst valued people, will get 1. And this definition allows for ties in between, where the sort of trivial rank that allowed everyone to be tied would give value R of x equals 0 to everyone. And so I'll recap sort of the way that we can connect predictors to rankings. We can start with a predictor and translate it into a ranking. That's what we'll call the induced ranking. So a little bit more formally, we can write out sort of how we would define this. But it basically requires just the comparison oracle. Given a predictor P, we can sort of define the rank of an individual according to the probability that their score is less than a random individual. And again, we said that given a ranking, we can define a handful of consistent predictors, a whole set. And so essentially what we're requiring here is some sort of non-crossing assignment of the values. And we can formalize that using the following definition, where we'll say that a predictor is R consistent if sort of when two individuals receive the same rank, then they receive the same predictions in this predictor. And when they receive different ranks, then the predictions respect the order or will also allow for ties. And so our setup will be similar to the one that we were using for prediction, where we're going to say that we're given a training sample. And again, we're going to be given binary outcomes in 0, 1. And even though we're given these binary outcomes, our goal will be to recover a ranking that's close to the true ranking, this ranking induced by P star, by the Bayes risk. And the challenge then is that these 0, 1 outcomes provide rather unreliable evidence about the pairwise comparisons on individuals. You can imagine that if I flip two biased coins, one comes up heads and one comes up tails, how should I know what evidence do I have about the actual biases from a single coin flip? You can work it out, but the point is that there's still significant uncertainty, and that very likely you might get heads, heads, tails, tails. In which case, there's really not that much information that you can glean from it. But the observation is that actually these statistical queries that we were working with before over large groups actually do provide better evidence about pairwise comparisons across groups. So because the statistical queries, or these expectations over large groups, will concentrate about their mean, then we can hope to say something about the pairwise comparisons between groups, given only access to a binary sample. So to motivate our notions of fairness in rankings, let's go through a different toy example. Suppose again we have a population S and a population T. And in this example, I'm going to say that the expectation on S is 0.8 and the expectation on T is 0.2. And I'll sort of switch to a shorthand that will make it easy, my life easier. So if that's all you knew, if those were the only statistical queries that you knew, then somehow a reasonable ranking might be to put all of S above all of T, that they really are the most qualified according to these tests. And an alternative ranking that put all of S below all of T really feels unreasonable. In particular, the ranking favors T over the group S, even though our statistical tests tell us that at least on average, S is more qualified than T. And so this is the type of reversal or that we want to, this is one form of inaccuracy that feels blatantly unfair, that somehow you're favoring a group T that is obviously less qualified than the group S. And so this leads us to a notion of domination that generalizes the idea of completely being above, one group being completely above the other. So we say that a group T dominates a group S within a ranking R if there's a matching between the group T and S, such that sort of it's a downward pointing matching, that all of the matched individuals in T are better than those in S. And sort of this is a very combinatorial way to understand it. The notion that we actually work with is slightly more technical, but is some notion of approximate CDS domination, essentially. That the probability that a random member of T is ranked better than that of S is never worse than gamma. So throughout, I think it's probably easiest to think of this gamma as 0. So basically, the point is that the probability that that at a given threshold, tau, the probability that the member of T is above this threshold, is better than this threshold, exceeds that of S. And so the concern is that T would dominate S within a ranking, but the expectations would disagree with this domination relation. That's to say that T would dominate S, but the statistical queries would provide evidence that somehow this is a misranking. And so we can actually formalize that intuition with a lemma that says that if T, gamma dominates the group S within a ranking R, then for every predictor that is consistent with R, then actually the expectation of this predictor on T is larger than that of S, at least up to this gamma factor. And so I think in the interest of time, I will skip the proof of this, but I think the main point to highlight is that it gives you a way to connect between predictors and rankings, and shows you how to use these connections. But the takeaway is that if T dominates this group S within the ranking, but the expectations are different, then somehow we have clear evidence that this ranking R is violating the evidence at hand and is not the true predictor, or not the true ranking. So with this in mind, we can then sort of introduce a new definition of fairness for rankings, which aims to prevent this systematic misrepresentation of groups within a class again. So rather than just reasoning about one group S and one group T, we're going to define and apply this multi-group perspective. So we'll say that a ranking is C domination compatible for a collection C if for all pairs of sets S and T within this class, if T dominates S, then the expectation of T should really be larger than that of S, right? Somehow that it's consistent with the evidence. And we'll require this simultaneous compatibility across this rich collection of subpopulations. Again, we can define a sort of a more approximate notion that is more technical than probably we need in this talk. But the takeaways and somehow corollaries of this lemma are that if a ranking is not C domination compatible, then what we know is that there's no predictor consistent with the ranking and simultaneously consistent with the statistical queries on C. Which is to say, just by contrapositive, if a predictor is consistent with the evidence in C, then the induced ranking must be C domination compatible. And so the observation we make is that actually these C multi-calibrated predictors are also C evidence consistent. They respect the expectations that in the tests required for domination compatibility. So what this result amounts to, or what this observation amounts to, is a theorem that says that the induced ranking of a multi-calibrated predictor actually will be domination compatible. Which is to say that one way that we can get our hands on a domination compatible ranking is to first learn a multi-calibrated predictor and translate it into the induced ranking and we will inherit the domination compatibility notion. While I don't have time to get into the details of this, what we can actually observe is that even a weaker notion that we call multi-accuracy, basically unbiasedness across all of these subpopulations, suffices for this result. That actually a multi-accurate predictor induces a C domination compatible ranking. And what this observation does is it actually highlights a weakness in domination compatibility. So even though domination compatibility aims to try to get at the idea that we want to make sure that we're not misrepresenting groups within this class, let's go through another toy example that maybe highlights a weakness here. So again, I'll have a group S and a group T, but in this case, S is sort of almost perfect. Their expectation is 0.99, and T will only be 0.5. But what I'm going to do is split T into two groups, arbitrarily, let's say randomly, or such that the expectation in T1 is still 0.5, and the expectation in T0 is still 0.5. And of course, the group S, the expectation is still 0.99. So this ranking clearly favors some members of T above S in a way that feels wrong, that feels arbitrary, and in a way that flips their expectations. But still, when we look at the domination compatibility conditions, we'll note that actually T only 0.5 dominates S. Basically, by the time that, by this point, there's sort of 0.5 of T's mass, but then quickly all of S gets covered. So the domination compatibility requirement only requires that the expectation of the group T be larger than S after adding 0.5. And so what we see is that actually this ranking, this inequality holds. Therefore, domination compatibility between S and T holds. So what we can see is that R actually seems to still misrepresent the relationship, at least between part of T and part of S, but satisfies this notion of domination compatibility on the groups S and T. And so the observation that we need here is that actually the ranking itself seems to define some important sets, right? This group T1 and T0, they didn't actually exist. We made them up in our minds, and they were only defined by the ranking in question. And so the point is that if we incorporate our knowledge of what the ranking is doing to define new sets and new statistical queries, then we can actually improve the guarantees of domination compatibility significantly. So we'll introduce yet another definition and say that a ranking is C reflexive domination compatible if it is domination compatible not just on the sets defined in C, but on the sets that are defined as sort of by the sets in C, as well as on the intersections of the individual supported or receiving a certain rank prediction or a rank tau. And so hopefully this looks very familiar to notion, sort of what we're doing in calibration and multi-calibration as well. So just to quickly note, what this does is that it then introduces these groups T1 and T0 into the groups that we are willing to reason about and that we have to reason about in order to achieve domination compatibility in this reflexive way. So then we can say that T1 0 dominates S, but the expectations don't respect that relationship, which is to say that this ranking that we proposed actually fails this, this stronger reflexive domination compatibility notion. And so I'm running out of time, but the punchline is that in fact, this stronger notion of domination compatibility, this reflexive notion of domination compatibility, is actually essentially equivalent to multi-calibration. You have to do some work to understand what it even means to translate between a predictor and a ranking here. But the point is that domination compatibility in this stronger sense and multi-calibration, even though they're defined in very different ways, are essentially encoding the same notion of evidence-based fairness, that you're not mismatching groups. And so to conclude, basically the point is that in order to learn a ranking, if you want a domination compatibility ranking, what you can first do is learn a multi-calibrated predictor and then translate it into a ranking. And what our equivalence shows is that essentially this reduction is unavoidable. That if you were to somehow learn an evidence or a domination compatible ranking some other way, then essentially you've already learned a multi-calibrated predictor as well. And the other and maybe more important point here is that studying these rankings gave us a new lens on multi-calibration. In particular, we've shown an equivalent way to characterize multi-calibration through this semantic notion of domination compatibility. And what that really shows is that it supports this idea that multi-calibration really requires good global learning, that it satisfies a number of properties that we would expect from a fair and evidence-based ranking, not just a prediction desideratum. So just to speculate at a very high level, if I can have 1 or 2 more minutes, I think fairness is very context specific. And there's always this inherent tension in the choice of notions that you choose. If you choose too weak a notion, then you may risk certifying a model as fair when it's really doing significant harms. If you choose too strong a notion, it may delay effective and important and necessary interventions. And one appeal of this multi-group fairness notion is that it can really be tuned to your needs based on the available data and computational resources by choosing an appropriate class C. But rather than, even though I do think this notion of multi-group fairness is quite appealing, I think more than striving for some one definition to rule them all, I think we really do need to assemble a toolkit of different fairness notions, where we articulate desirable properties and try to understand the connections between them to best understand when we should apply them in practice. And so this talk focused predominantly on learning both a predictive model and a ranking, but there's certainly many other aspects to sort of the machine learning prediction pipeline, from identifying the task to collecting training data to making decisions, and then to understanding the loops and connections between all of these processes. And so I think certainly there's a lot of exciting work to be done in this area. Yeah, great. So I'll stop there, and thank you for your attention, and happy to take any questions.
Thanks, Mike. Is there any question? If so, feel free to unmute yourself and ask them.
Hi, yeah, I have a question. I was the one who had asked earlier about, you know, whether there exists some sensitive attribute. And I think maybe I should try rephrasing it at a little higher level. I guess I'm wondering if there's any sort of like no free lunch theorem with regards to fairness in training settings. So let's say you have some sort of set group that you care about, and you train your thing, and it's pretty fair. But then we realize, oh, maybe there's another division that we also care about. Is there, for any train model, is there some other collection that's guaranteed to be sort of unfair?
Great. So it's a good question. And the way that I would try to understand it is that multi-calibration and these evidence-based notions are really focused within this rectangle, so learning the predictive model. And what we have to assume for our learning algorithms is that we're getting access to sort of bona fide, unbiased training data drawn from according to P star, according to this sort of Bayes optimal predictor. And so with respect to once you get this Bayes optimal predictor, then you are calibrated. The question then is sort of what features were included in your predictive model, and what this Bayes optimal thing actually is. So in a sense, like you will always be uncalibrated a posteriori on the individuals on whom you made mistakes. And so I think there's issues that if you then introduced a new feature that was not incorporated into the original predictive model, then this could highlight a new set on which you would be miscalibrated or inaccurate.
I see. So the sort of no free lunch-esque theorem is pretty trivial. It's take all the elements that you made a mistake on, make that your subset, and you're maximally bad.
Yeah. So exactly. So this notion of calibration is very much an a priori notion.
Right.
Right. Yeah.
And whether or not that subgroup has any coherent meaning to an external person is a different question.
Exactly. It's parameterized by the features that you're observing when learning. Right. Sort of what looks random is parameterized by what information you have in your features.
Sure, makes sense. Thank you.
Yeah. Thanks for the question.
I have another question, which is, so here the correspondence with agnostic learning is in the regular pack learning, I guess, statistical learning framework. Have you considered whether there is a connection or maybe like some speed up possible or whatever in the in more like active learning kind of framework? Since it seems like a lot of what you want to do is focus on these small subpopulations where you by definition can't afford to make errors. So is there like a more interactive model of learning where this could that could help for the task?
That's an interesting question. I'm not super familiar with the active learning literature, so I can't speak to just sort of whether that's even possible. But given that one could sidestep sort of hardness in learning results with active learning, it's a good question, right? And I imagine that if one could, then we do have some sort of equivalence. So whenever you can perform this, basically we need some correlation detection. We reduce the problem of searching for a subgroup to detecting correlations. And so anytime you can detect this correlation and in this weak agnostic sense over this class that you have, then you can perform the auditing and iterate and learn. So It's a good question. Point being, if you can do this active learning, then you should be able to leverage it for multi-calibration.
Thank you. Is there any other question? If not, I'm gonna take us offline, and you can still stay a little bit and ask questions that you might not dare asking, but I'm gonna stop the live stream.
Great, thanks so much.